It will be available early morning on Wednesday, basically 12 a.m. until late night on Wednesday, 11:59 p.m. So when we have our lecture on Tuesday, again, make sure everybody understands this, right? When next week we have our lecture on Tuesday, it's going to end at, let's say, around 10 p.m. It's going to be 11 p.m. And then when it's 12 a.m., that's now Wednesday. So that's when the test becomes available. If any of you want to take it right away, you can. Or you just wake up Wednesday morning and then before work, after work, if you have work at any time before Wednesday, 11:59 p.m., that is when you would have to submit it. Now, submission is two parts. There is the MML part, which is for all of your answers. That's basically like boxing up your answers on your paper that you would turn in if it were in person. And then all the work leading up to those answers will be submitted through Canvas by uploading a scanned version of your work. And you definitely want to practice that with your study guide. So your study guide is also, we discussed it on Tuesday, that's available. And the submission is just the work through Canvas. And you can find it in Canvas assignments. Same place where on next Wednesday you'll find the submission link for the exam as well. But I really encourage you to try and do the study guide over the weekend and try to upload it maybe on the weekend or on Monday, so that if there are issues, you still have time to fix those issues. You still have time to maybe talk to other people in class or talk to me, or before the actual exam is due. Because if you're going to procrastinate, if you're going to try and just for the first time upload this stuff on Canvas, then you run into any issues, and then there's not enough time, then you're going to miss out on the exam, and that's not something you want to do. So anything that I need to clarify what has been said on Tuesday or today about the exam or the study guide, anything that you guys still have questions on? No, everybody's good. All right, you'll still have time to message me if something comes up, but hopefully everything made sense. So let's go ahead and then start on our lesson. And I'm going to use my graphic software part, just like it better. And where is it? There it is. Okay. First lesson is for polynomial functions. We introduced polynomials in algebra, so a lot of this would seem familiar. We already introduced a couple of polynomials here in this class without really calling them polynomials. Now, f of x, mx plus b, that's something that we have seen. Linear functions, f of x equals ax squared plus bx plus c, that is something that we have seen. Quadratic functions, that's what we did, I think, last week and partially this week. Or we actually did both of them this week, now that I think about it. So what we want to do is we want to extend this pattern and just add on more terms with higher exponents, right? So next option would be something like f of x equals, if I call it ax cubed plus bx squared plus cx plus d, and then kind of keep going. But you can see that it gets pretty annoying by just going over all these alphabet letters. So instead, we adapt a format which becomes a much easier format to use to generalize this type of a function. So instead of mx plus b, for example, we would use f of x equals a sub 1x plus a sub 0 or a naught for our constant, and a sub 1 would be the coefficient for x to the first power. For the quadratic function, we would say a sub 2 x squared plus a sub 1x plus a naught. So you see that our coefficients, instead of being a bunch of letters of the alphabet, we just use letter A with a subscript, and the subscript corresponds to the exponent that that coefficient belongs to. So a sub 2 belongs to x squared, and a sub naught actually also belongs to x to the power of 0. We know x to the power of 0 is 1. We don't write it, so there's still that pattern there. Everything corresponds correctly. So if I wanted to do that for this guy, instead I would have f of x equals a sub 3 x cubed, a sub 2x squared, a sub 1x plus a naught. And then dot, dot, dot becomes a little easier to generalize. Then I can say, let's define a polynomial function using this format, and it's going to be f of x equals. And notice how for all of these, we would put them in decreasing order of exponents. We start with the largest exponent and then go down to smaller, smaller, smaller until we reach the constant term. So that is the format we want to use for our polynomials. And if the largest exponent is some number n, then the coefficient corresponding to that is a sub n times x to the power of n. And then we keep decreasing our exponents. So 1 less than that would be n minus 1. And the power also goes 1 less, and then 2 less and 3 less, but we would just say dot, dot, dot until we get to a sub 1 x to the first power, and closing it off with the last term, the constant term a naught. So this would be our format for polynomial functions. And you see again that the order of our terms follows a decreasing order of exponents. That way, this first term here is it's called a leading term, and it's going to help us determine quite a few things about these polynomials. So the term a sub n x to the power of n, the one that has the largest exponent, that is referred to as the leading term. And the leading term contains two pieces of information. One of them is the leading coefficient. So a sub n is the coefficient of this term. That's called the leading coefficient. And the number n here, the highest exponent, that is the degree of our polynomial function. So n is the degree of the polynomial. Now, some requirements that were established back in algebra in order for this to be a polynomial, our n's, our exponents, they have to be positive integers. So I'm going to add that on here. Exponents are whole numbers. So that means they're positive integers. And coefficients just have to be real numbers. So they could be fractions, they could be radicals, everything is fine, everything goes as long as they're not complex numbers. So coefficients are real numbers. Now, if I gave you a couple of examples, if I say f of x equals 1/3 x cubed minus 7x squared plus 5x minus square root of 3, is this a polynomial? Does this qualify to be a polynomial function?
Yes.
Yes.
Yes, yes, it does, because our exponents here are 3, 2, 1, no exponents, so 0 basically. Those are positive integers. Our coefficients can be fractions, radicals, integers, everything is fine. So this is a polynomial. Polynomial. If I gave you something like g of x equals negative 5x cubed minus 7x to the negative second plus 2x minus 5, would this still be a polynomial?
No.
No.
This
No.
one would not be, and reason being is this exponent, right? So exponents have to be positive integers, or if I had something like 1/2 or 1/3 for an exponent, also we would say not a polynomial because of that. Now, we will be graphing in the next lesson, but in this lesson we can describe a couple of things, a couple of properties for polynomials. One is the domain of polynomials is all real numbers. So the domain is always all real numbers. I can plug in any value and I'll get a real number as a result if I have a polynomial. The range, not so much. So for the range, we're not going to generalize it. Range is sometimes all real numbers, sometimes it's not. So we're just not going to say anything about the general case. We will determine it based on specific examples when necessary. We also want to mention that the graph of a polynomial is always going to be a smooth, continuous curve. Except unless you have a linear function, which is also considered a polynomial, then it's not really a curve, it's a line. But for other cases, it is a smooth, continuous curve. So smooth means there's no sharp edges, there's no V shapes. It cannot do something like this. It cannot be nice and smooth and then do something like that. Right? This part would be considered breaking a polynomial. It's not going to have that V shape. Continuous means you can draw it without lifting your pen or whatever you're writing with. So this is no go. And if you then have a discontinuity of some sort, like you jump from one point to another and start back up, then that also would not fly, because here you have discontinuity. So for our polynomials, it's always going to be a nice curve, a U shape for parabolas. We've already seen those W shapes. So things like this are okay. Right, so this is a smooth continuous curve, or something that looks like this. This is a smooth continuous curve. So those are the types of curves that we're going to encounter. And we will break down different components of these curves. And then in 4.2, in the next lesson, we will actually graph them. So the first component we want to break down is what's referred to as the end behavior. And behavior of a function. And behavior describes as to how your function values behave as your x values grow really large, go to infinity, or really small, go to negative infinity. So does your function, and for polynomials, there is not too many choices. Your function values can either go forever up to infinity or forever down to negative infinity on either side. So there's not too many choices, but there's still some choices to consider. So end behavior talks about function values, which means y values, right? Function values are y values as x approaches infinity and as x approaches negative infinity. So on both ends of your number lines, basically, the notation that we use or that we can use is as x goes to infinity, what happens to my function values? And the options are going to be either positive infinity or negative infinity, depending on a few things. And also the other end of the spectrum, as x's go all the way to the left, to negative infinity, what happens to my function values? Where do they go? Also two options. They will either go to positive infinity or negative infinity. So you can kind of tell that there's only four options here, right? The four options are, you can have the left side. So let's try and do these little graphs. So one option is you have, as you go to infinity, so infinity is again here, right? To the right, positive infinity, to the left is negative infinity. So as you go to infinity, one option is that your function values also go to infinity. And as you go to negative infinity, your function values still go to positive infinity. So that would be one option. The other option is they will both go to negative infinity. The third option is as you go to infinity, function values go to infinity, but as you go to negative infinity, function values go to negative infinity. Or as you go to positive infinity, function values go negative, but as x values go negative infinity, function values go positive. So those arrows are basically describing the end behavior, not the mid behavior or whatever you would refer to it, the inside behavior, right? Because here this could do, this could do that, or it can have just one hump, or it can have a bunch of humps, right? So there's a bunch of things that can happen here. It could do, something like that. But we're only for now discussing what happens towards the ends, towards infinities. And that's what we refer to as end behavior. So if I were to use this notation, right, there's these are the four cases that we have. So let me draw some lines here so you can see it a little clearer. So these are the four cases that we have here. And if I were to use the notation x approaching, y approaching, this would be as x approaches infinity, f of x also approaches infinity. As x approaches negative infinity, f of x still approaches positive infinity. First case. Second case, as x goes to positive infinity, functions go to negative. As x goes to negative infinity, function values go to still negative. This guy, as x's grow positive infinity, so do function values. As x go to negative infinity, so do function values. And this guy is kind of the reverse of that. As x's go to positive, function values go negative. But as x's go negative, function values go positive. So these are the four cases. Now, what determines which case you're looking at are two factors that we discussed earlier that come from the leading term. It's the leading coefficient and the degree. So the first case occurs if you have positive leading coefficient, and if you have even degree. Then you know it's going to be this case. The second case occurs if you have negative leading coefficient, but still even degree. Huh, what is that little square? How did that get in here? I have no idea how I did that. Get out of here, little square. All right, negative even. The third case is if we have positive but odd degree. And the final case is negative leading coefficient, odd degree. So those are the four cases in sort of in more detail. For me, the shorter way of writing all of those four cases is to make a little chart that describes the four cases. And the chart looks like this. I either have even degree or odd degree, and I either have positive lead coefficient or negative. So, and I'll just draw pictures here. I know if it's positive even, then that's my end behavior. If it's positive odd, then that's my end behavior. If it's negative even, both go down. If it's negative odd, then reverse it. So that's sort of the generalization of what we've just discussed. Now, for your homework, I think you might have to use the notation where you write f of x approaches infinity or negative infinity. So that's why we still have these here for you to look at. All right, so that's the end behavior. That's how your function is going to act on the outer edges. But what happens in the middle, in between, that's also pretty important. Now, let's say we will know the end behavior, and the end behavior will tell us it's doing something like this. Sure, I can scroll up for a bit. So knowing the end behavior, we still want to figure out how it'll react, how it'll act in the middle. And for that, we will look at things like x-intercepts and also something called multiplicity, because when we have an x-intercept, there's actually a couple of things that can happen on an x-intercept. Right, so we want to know, well, does our function, if I have, for example, my x-axis here, and let's say I have some x-intercepts, I want to know, does my function cross at an intercept, or maybe just touches at an intercept and does something like that? And that'll be something we can determine algebraically in order to help us with the graph. And also we will be able to consider how many possible turns does it make? Does it have a couple, or does it do, a whole lot in between? Then, of course, we would see that there's a lot more x-intercepts. So x-intercepts are pretty important in figuring out the middle behavior of the function so that we can then graph it better. We're still not going to have exact graphs. As a matter of fact, for your homework, I'm pretty sure you won't have to graph. You'll just have to choose the correct option of like a multiple choice type of question. You have to choose which is the correct corresponding graph. And it seemed to be pretty straightforward when I looked at it. So I think that'll be fine. And so when we talk about the middle portion of the graph, what happens between the two tails, we want to introduce a concept called a zero. So real zeros of a polynomial. Real zeros of a polynomial. Now, basically every single one of these concepts is something that we already know, something that we've discussed, but we never maybe called it by a specific name. Now we're going to call it by a specific name. So we're going to say that, let's see, which letter do I like? Let's say A. Well, no, we already used A. I guess the book uses R, so I'll use R. So R, and that's my R, by the way, is a real zero of a polynomial f of x. We'll call our polynomial f of x. So now we're saying that R is a real zero, so we're defining what it means to be a real zero, and it means any of the following things. So we're going to have basically 4 different bullet points here, and they're all equivalent. The one that we probably will use most often is how to find the real zero if we have an equation. It is a solution when you let f of x equal to 0. So R is a solution to equation f of x equals 0. That's how we will find our zeros. Again, this is my R. A lot of times people complain that my R's look weird, but yeah. The next part is with graphing. Actually, let's do a factor first. So a lot of times if we were solving quadratics, we would try to factor. If it didn't factor, then we would have to be using a quadratic equation. But for those that did factor, we probably noticed something, that if you're solving, if you're solving x squared minus 5x minus 6, if this is your polynomial, and if you're trying to solve the equation f of x equals 0, then it's really solving this guy, x squared minus 5x minus 6 equals 0. And if it factors, then that's an easier approach. So in this one, we could factor as x minus 6, x plus 1. And then from these factors, we would get solutions. So solution R corresponds to a factor x minus R, right? X minus 6 would result in solution x is 6. X plus 1 would result in solution x is equal to negative 1. So that's what we're saying here. If R is a solution, then x minus R is a factor of f of x. If we have solutions that are integers, it's pretty simple to see that. But remember, they don't have to be integers. Like if this were a quadratic equation that we had to use on it, and we would get something like negative 7 plus minus square root of 13 over 5, or whatever we would get. Those are 2 zeros. They're still zeros. They're still real zeros if they were solutions to some equation. And x plus or minus that 0 would be a factor. So that's something to keep track of, that even if we don't have a nice integer solution, we still know it corresponds to some factor that it came from. Now, the last part deals with graphing. We knew that if we had to graph this quadratic equation and we had to find x-intercepts, this is exactly how we would do it. We would say to find x-intercepts, we need to let y equal to 0. But that's exactly solving equation f of x equals 0, which we just did. So these real zeros, they're also the x-intercepts. So that's the 4th bullet point here. 0 comma r. Oh, no, that's not right. R comma 0 is x-intercept of the graph y equals f of x. So if I were graphing this polynomial, whatever it may be, then those real zeros are the x-intercepts. So again, all of these 4 bullet points, they're the same thing. They're saying the same thing, but in different contexts, we would use the appropriate bullet point. So if we have a 0, that means it's a solution. That's how you usually find those zeros. If we need to write an equation, then we would go from 0 and use a factor that it came from, and then multiply all those factors. Or if we're graphing, then we would use the fact that they're intercepts, they're x-intercepts. Right, so just going back to this example, if this is my polynomial, and I found my zeros, so zeros, I can now use this notation, and this word 0, or zeros rather, there's 2 of them. 6 and -1, those are my zeros. That's what we call them. I also know that from these zeros, I can say, well, x minus 6 is a factor. And I know that x minus -1, which makes it x plus 1, these are factors of my polynomial. And I kind of knew it already because that's how I solved it. But even if I didn't have it, I just had the zeros, then I know the factors that they come from. And we also know that 6, 0 and -1, 0, those are x-intercepts if we try to graph it. So again, most of these concepts we already were familiar with. Now we're just giving them sort of a newer name. They're all called zeros. All right, so let's use at least some of these concepts and look at number 44. And here we want to write the equation of a polynomial containing the given zeros. And the zeros for 44 are -4, 0, and 2. So now the word 0 can mean a couple of things depending on what we're using, right? If you're saying the number 0, that just means the value of 0. Or if we're saying 0 of a polynomial, then that now means something else. So here we're stating that these are zeros of a polynomial. One of them is the number 0. And our goal is to write an equation. So what we would do is we would say, if x equals, so if -4 is a 0, it means x equals -4 was a solution to the equation f of x equals 0. And this comes from a factor. X equals -4 comes from a factor x plus 4. And we can do the same thing for the remaining zeros. X equals 0, that's x minus 0, just x. And x equals 2, that comes from a factor x minus 2. So these are the factors that my polynomial would have to contain. And if I want to write my polynomial, I can then say, well, f of x is just the product of these factors. And then depending if I need to simplify it, depending on the directions for your homework, it'll probably say simplify, so you'll just have to multiply it out. So f of x equals x times, FOIL this out, x squared plus 4x minus 2x, so that's plus 2x minus 8. F of x equals x cubed plus 2x squared minus 8x. So this would be one possible answer for a polynomial, but there could be infinitely many different answers unless the question will specify not just the zeros, but also where or which point will the polynomial go through. Because if I take this f of x, remember, if I multiply it by, if I say f of x can equal to 10 times, or let's call it g of x instead of using f of x. 10 times whatever f of x was, this will have exactly the same zeros of -4, 0, and 2, because multiplying by 10 will not change my zeros. If I were to solve it, my factors wouldn't have been any different. If I had a 10 here, I would still have the same exact zeros. So that's why there's infinitely many answers, unless there's a specific point that you have to cover, and some of the homework questions will tell you, oh, there's a point that you have to go through. Then you'll have to find what your coefficient would have to be. But in this case, it did not, so this is one of the possible answers here. All right, now we have to discuss something called multiplicity. This concept of multiplicity basically talks about repetition of zeros. How many of those zeros, how many of each of those zeros did you have? Because if I had a polynomial that looks like this, x times x minus 3, for example, or if I had a polynomial that looks like this, x cubed x minus 3 squared, the zeros would be absolutely the same, right? The zeros of f of x would be 0 and positive 3. What would be the zeros of g of x? Do these exponents change my solutions if x cubed?
0 and positive 3.
Yeah, so these exponents, they don't change the actual solutions. The only way x cubed is equal to 0 is if x is equal to 0. The only way x minus 3 squared is equal to 0 is if x minus 3 is equal to 0. So those do not affect my actual zeros. It would still be 0 and positive 3. But it makes sense that the graphs would have been different, that these aren't the same function. So we have to be able to differentiate between, well, where do they come from? Which factors do they come from? And that's where multiplicity comes in. For example, for f of x, this 0 here would have multiplicity of 1. And this 3 here would also have multiplicity of 1. Because they came from a single factor. This was x to the first power. This was x minus 3 to the first power. But for g of x, this 0 would have multiplicity of 3. This 0 would have multiplicity of 2. Because they came from the corresponding factors. One of them was to the third power. The other was to the second power. So that's really all that multiplicity is. It tells us, where did those zeros come from? Did the factor, was it just a single factor, or were there multiple exponents, multiple iterations of that factor? And if there were, then the largest exponent is the multiplicity. So what I mean by largest exponent, if I write g of x as x times x squared times x minus 3 squared, this doesn't change the fact that I have 3 factors of x, so the multiplicity coming from that factor is going to be 3, even if I didn't simplify it right away. So this has to be simplified in order to get the correct multiplicity, and that's where the definition comes in, that it's the largest possible exponent of that factor. So I'm going to write the definition in words as to what we just discussed. So when we have multiplicity of zeros, that's what we're discussing, right? Multiplicity of zeros of a polynomial. And we define it in the following way. If we have a factor, x minus r, raised to some power m. So it's a factor of your polynomial. So if x minus r raised to the power of m is a factor of a polynomial, which we will call f of x, for example, with largest possible m. So this part here, that just refers to if you have the same base, the same factor, make sure that you combine them with the largest possible exponent, that you don't write it as x squared times x. Instead, you write it as x cubed. You don't write it as x minus 3 times x minus 3. Instead, you write it x minus 3 squared. So the largest possible exponent, largest possible m. Then m, this m is the multiplicity. Multiplicity of the 0 r. Right, so again, if I have a factor x minus r, it has a corresponding 0 r that came from that factor, and then the multiplicity is the exponent. Let's just do one more example to make sure that all made sense. State all zeros along with their multiplicity. And let's make something up. Let's say we have g of x equals -7, and I'll give it in factored form to keep things a little easier. X cubed times x minus 1/3 squared times x plus 5. So let's say this is our function. Also, let's do another part to it. Let's do part A this, but part B we're gonna do something else. Part B we're gonna say find the leading term. Find the leading term. Your book describes this when it says find the leading term. It says something like, what does the function behave as when x's approach infinity, or something like that. But that's basically finding the leading term. So for part A, we are looking for our zeros and their multiplicities. So this -7 doesn't change the zeros, because -7 is a numerical factor. It's not going to give me any solutions. So we only consider the factors that have variables in there. So x cubed, we consider x equals 0. And because it was x cubed, then the multiplicity of that is 3. So the 0 is 0, and the multiplicity is 3. The next factor, x minus 1/3, x equals 1/3 is the 0. Multiplicity of 2. And the last factor, x plus 5, we set that equal to 0. X equals -5, and that one is multiplicity 1. And that's really it as far as multiplicity goes. Yeah.
Why is it that the first one is x equals 0? Wouldn't it be x equals 7?
So we're solving the following equation, right? We could include the -7 in solution here, right? But I can just say divide both sides by -7. So that's how we would get rid of the coefficient, whatever it may be, because 0 divided by anything is still 0.
Yeah.
And then x cubed equals 0. You can either say cube root both sides, or you can just say, well, what number to the exponent, to any exponent really, will give us 0, and the only way is 0, right?
Thank you.
Yeah, we're multiplying. -7 is being multiplied. It's not x minus 7 cubed. If it was x minus 7 cubed, then it would be x is 7. but here it's a coefficient. All right, so we got our multiplicity 3 for the 0 of 0. We got multiplicity 2 for the 0 of 1/3, and we got multiplicity of 1 for the negative 5, 0. All right, the next step is finding leading coefficient, and then we're going to talk about how this all comes in together. For the leading coefficient, we don't need to multiply out the entire polynomial. I have my negative 7x cubed. I have my x, and then I'm just going to put, well, I'm going to find the whole thing for now. But this square, I know is going to give me x squared for the first term, and then a bunch of other terms, 2 other terms, but what matters is the highest exponent. So I'm only going to worry about that guy. Here, also x plus dot, dot, dot. I don't care about the 5. I don't care about what happens when I square and get the other terms from my middle factor. I just care about these guys, because when I multiply them out, I'm only looking for the term that has the highest exponent. So when I multiply these out, the x cubed will be the highest exponent, and then sure, there will be a bunch of other terms there, but again, don't really care about them for leading term. That's what we're doing here, finding the leading term. And finally, when I distribute, this will be negative 7x to the 6. Again, remember, when you multiply, you have the same base, you add your exponents, and then sure, there will be a bunch of other terms, but this is the guy that has the largest exponent. So this would be the leading term, and from it, I can say that the degree is 6. It's even, because we'll need that. Leading coefficient is negative 7. Negative, we will need that for end behavior. And as far as multiplicities go, we can now discuss how do multiplicities sort of factor into the graphing of polynomials. All right, so the next little discussion is multiplicities again. If I have a graph and I have my x-intercepts, say I have one here, let's say I have one here, there's 2 ways that an intercept can behave. One is we cross, so whatever my function did, we cross. The other is we touch. Right, so when we have an x-intercept, make it bigger, we bounce off of it in some cases and we cross it in other cases. And that's what multiplicity determines. If we bounce off, it means we had x-intercept that came from an even multiplicity 0. If we cross, that means we have an x-intercept from odd multiplicity 0. And you can kind of think about it in terms of the basic functions x squared and x cubed. Let's call it g of x. Right, if I were to graph x squared, so let's do a little bit of side note here. If I were to graph x squared, that's what I would get, right? But now we know it's a parabola, but now we can think in terms of zeros, right? This x squared would have a 0, x equals 0 with multiplicity 2, even multiplicity. So this x-intercept, because remember 0, x-intercept, those are all synonyms at this point, we should bounce off from that 0. Multiplicity is even, works out. X cubed, we know that the graph of x cubed does something like this, right? It crosses at 0, 0. Here, x equals 0 is multiplicity, not cube, but multiplicity 3. Odd multiplicity, we cross. So if you forget which one's which, just think of x squared or x cubed, and that should help you with that property. All right, so now we have and behavior set up. We have multiplicity and how it relates to the graphing. That's also set up. The last part we're going to mention is a little bit about turning points. So turning points are basically these guys. If you have your curve and behavior, these are the turning points where you change from increasing to decreasing. So they're like humps. So turning points is the proper name for them. Hump, like camel hump, is what I sometimes call them. Not a very proper definition, but sometimes I'll refer to it as humps. So these are where the graph changes, basically changes direction from increasing to decreasing, because as we look here, we're increasing as we reach this hump. Then we start decreasing as we reach this one. Then we're back to increasing, and so forth. So one way we can talk about them is that's where graph changes direction from increasing to decreasing. But we can also tie it to a notion that we've discussed earlier. What are these red points? Using vocabulary that we were discussing in chapter 2 for properties of functions.
Minimums, maximums.
Yeah, these are local maximas and minimas, right? They're not necessarily absolute. Some of them might be, or we might not have an absolute one, depending on what the function does, but they are definitely localized. Like if we localize our domains, then those points are exactly maximas and minimas. So these are turning points, are also local max and local mins. And also we can state that if a polynomial has degree n, so for polynomial of degree n, the graph will have at most n minus 1 turning points. At most n minus 1 turning points. To prove that in calculus, it'll be probably like 2 lines of a proof. So it's a pretty easy proof as you learn more concepts in your next class. But for now, we just take it as a as a theorem without a proof. So if you have degree 5, then you could have at most 4 turning points, and so on. All right. Now let's go ahead and do a couple of examples. Let's see which one do I like. think 62, well, might be too easy. Let's do 60. We're given this polynomial f of x, and then we have to determine a few things. We don't have to graph it just yet, but soon. X plus 4, x plus 3 cubed. And we'll do them one part at a time. So part A says list all zeros and their multiplicities. And these are going to be given to you in factored form, makes it a lot easier. So to find the zeros, we would solve the equation f of x equals 0. Our equation f of x is 4 times x plus 4 times x plus 3 cubed. Again, this numerical factor, it does not produce any zeros. I can simply choose to and say, I can divide by 4 on both sides, right? These will just disappear. Or I can simply ignore it for the purposes of finding zeros. So I'm just going to ignore it, and I'm going to look at all the factors that contain a variable. So x plus 4 equals 0 and x plus 3 equals 0, keeping track of the exponents. Here we get x equals negative 4, and what is the multiplicity for negative 4?
1.
1. Multiplicity is 1. Here x equals negative 3, and the multiplicity is 3. Yeah, multiplicity is 3. Both are odd, because when we need to graph, we don't really care if it's 1 or 3 or 5, we just care if it's odd or even. So definitely remember what it means to be odd or even. So these are, of course, odd. 3 and 1 are odd. So that's part A. Let's keep going. There's like 4 parts to this. Part B says determine whether the graph crosses or touches the x-axis at each x-intercept. So I'll just do the following. I'll say part B, list x-intercepts, and then we will say cross or touch. But we know that x-intercepts are exactly the zeros. So I have x-intercept at x equals negative 4. Or you could also state it as negative 4 comma 0. But for the computer purposes, make sure you read what the instructions are. I think it'll just want you to type in the number, negative 4. So maybe I'll do that here for the example. And then, does it cross or does it touch at that x-intercept? That's the graph. What does it do? It crosses. Yeah, it crosses because it's odd multiplicity. The other x-intercept was negative 3, and also because it's odd, it'll cross. So that's part B. Part C says determine the maximum number of turning points. And actually, I would say that part D makes more sense to do first and then come back to part C. That kind of is how I see it. So I'm going to come back to that in a second. Part D says it says a few things. Determine the end behavior. Find the power function that the graph resembles for large values of x. So that's what we did a little bit earlier here. Over here. This is what we were doing. Finding the function that the graph resembles for large values of x. It's only the leading term that will determine the final resemblance. of the function as x's grow really large and really small. So that's what we're going to have to do. Just concentrate on the leading term here. Oh, my tablet is becoming pretty unresponsive. All right, so again, our original function was f of x equals 4 times x plus 4 times x plus 3 cubed. So here the coefficient does play a role. We can't simply ignore it because when we find the leading term, that part is going to be included. Right, so this would be 4 times and then x plus, and I'll just put dot, dot, dot. If I do x plus 3 cubed, the first term is x cubed, and then it's going to have a bunch more terms. Here, when I multiply these out, I'm going to get x to the 4th, and then a bunch more terms with smaller exponents, and distributing will be 4x to the 4th, plus, again, a bunch more terms, but this will be my leading term. So this is my leading term that my function resembles as x's grow to infinity and negative infinity. And from here, I can see that this is even multiplicity, and this is positive leading coefficient. So my end behavior should look like that, right? Both sides going up, or if I have to write it out using this notation of they're not quite limits, but the book calls them limits. So as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x also goes to infinity. And that's what we're describing here. And now, because we see the degree is 4, we can also discuss the turning points. And the turning points, there can be at most 3 turning points then. So at most 3 turning points would be the answer for part C. All right, so you guys will have a couple of those questions, and they're all factored, making it much easier. Remember, we're only talking about real zeros here, so if you get a complex solution, that doesn't count. That's not a part of it. So I'm going to give you guys a break, and I'm gonna let my tablet here cool down a bit. I think it's overheating or something because it's not acting right.
Professors, did you say that how do we get turning point 3?
So turning points is n minus 1 from the degree. So the degree was 4. Right, that's this guy. The leading term determines the degree. And the turning points is 1 less, at most 3. So that was something that we wrote a little bit above what we're doing now. If you'll scroll up, you'll see it. All right, so let me do this. Let me stop the sharing here. So it's 8 o'clock. 8, yeah, we'll do about 15 minutes. So 8:15, I'm gonna start back up. So yeah, about 15-minute break for you guys, and then we'll continue. All right, guys. So I am back. Hopefully, it's going to work a little better. My tablet here. So we got one more lesson to go. And that's going to be graphing of the polynomial functions. So we'll probably do a couple of examples on that. And this is 4.2, graphing polynomials. So there's a few things that we talked about, and those properties are going to be used when we graph. So the first step that you'd probably want to do is you want to find the leading term. Because from the leading term, you can then read off the degree, the leading coefficient, and also, if you need to, the number of turning points. And the degree and the leading coefficient, these two dictate the end behavior. So step one, we'll just get a bunch of information from there and then conclude with how many turning points we can have at most, one less, again, n minus one at most. And also the end behavior, that was the table that we had in the previous lesson, odd versus even, positive versus negative leading coefficients. Step two is going to be our zeros. Find x-intercepts, but because we're doing graphing instead of just zeros, we're going to refer to them as x-intercepts. So find x-intercepts and their multiplicity. And also find the y-intercept. So here we'll get a few points. Now we have end behavior, we have intercepts and their multiplicity. So from there we can determine whether we cross or we bounce off at any given x-intercept. So I'll put that in here in parentheses. Multiplicities cross or bounce from the x-intercept. Step three, if you were graphing these on paper in pre-calculus, then you would have to plot some more points, and this part can get pretty annoying. So I'll just say plot more points just to get a feel and an idea of what your graph does in between your intercepts. However, in our class, you won't really have to do that because it's pretty tedious, and you'd probably want to use a graphing calculator or some software to do that until you get to calculus class, where you would learn derivatives, and then the turning points, those maxima and minima, would be much quicker process to find them. So for now, I'm gonna say we're gonna basically skip this part. When we do our graphs here in the notes, I'm just going to estimate what it does. When you do your homework, again, you will be given some multiple choice options, and these points, these extra points, will not really be necessary. The end behavior and the intercepts will already determine the correct answer. So I'm going to say it's skip, or optional probably is a better phrase to use here instead of skip. So I'll say optional. And finally, the last step is kind of connect this whole thing together and graph. But again, it is still an estimate because we are leaving some parts out, but we'll get at least an idea of what we're working with. So we'll do a couple of examples here. I will start with number 8. We have following polynomial function f of x equals x minus 1 times x plus 3 squared. So the first part we're going to find is the leading term and then kind of work from that. For the leading term, I know that I have x and then just stuff. And then I have, when I square this, it'll be x squared and then more stuff. So it'll be x cubed plus other terms. But x cubed is my leading term here. From this, we can already read off a bunch of information. So what would be the degree of this polynomial?
3.
Yeah, the degree here would be 3, right? The highest exponent, which is 3, so that's the degree. And the number of turning points would be 1 less, so I'll make a note of that. Turning points at most 2. Turning points is at most 2. Degree 3 means it's odd degree, so I'll also make a note of that. My leading coefficient is 1, so that's positive. So from here, I can say that the end behavior for an odd degree function with a positive leading coefficient, it looks like that. Graphing wise, or if you want to describe it, you can describe it with limit notations, but I'm just going to draw a couple of arrows and then we have to figure out what does it do in between there, you know? So that's our end behavior. And for part A, we said that that's what we want, right? Turning points and end behavior. Or for step 1. They don't have to be done in this order, but I'll just do them in this order. So next we have our intercepts. For x-intercepts, which are the zeros, we know we have to solve the equation f of x equals 0. So I have x minus 1 equals 0, results in x equals 1. And this is multiplicity 1. And here I have x plus 3 equals 0, results in x equals negative 3. Multiplicity is 2. So then we have to remember multiplicity 1 means we cross. Multiplicity 2 even means we touch at that point and go back up in the same direction. So those are my x-intercepts with the corresponding behavior at the x-intercepts. I also want to state the y-intercept. To find y-intercept, we let x equal to 0, so find f of 0. F of 0, plug in to your function, we have 0 minus 1, 0 plus 3. So it's negative 1 times 3 squared is 9, that's negative 9. So I have my y-intercept at negative 9. Now I have a few points, so I'm going to start with my graph. And my pet here is getting slower and slower. So hopefully it'll survive for another example. So I have my points at 1 and at -3. A y-intercept at -9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I know my end behavior, right? I know that I'm coming in from here and I'm leaving out that way. And I also know that at -3, I'm going to have touch, and here I'm going to have a cross. So now I'm going to kind of combine those things together and try and get a approximation at least of what my function will look like. So I'm coming in here. I'm going to touch here. I have to cross at this point. Now, what I don't know is the following. I don't know if this will be actually a local minimum or, and I'll show you what I mean by that. Then I know I have to keep going in that direction. So this is an approximation because very well this function could have done this, right? So that part I'm approximating. My turning points are being approximated, but that's what I meant by the optional step, that you can plug in some points. So if I wanted to have a slightly better idea, I could plug in points at -1. I can plug in point at -2, and those values will help me figure out what exactly my function does. But again, on your options that you will be given for your homework, this will be sufficient information to determine whether, you know, which is the correct answer. So if we were graphing it by hand, then in class I usually instruct the students that I won't mark points off for the turning points if they're lower or higher where they should be, but I would mark points off for wrong end behavior or for wrong intercepts and their multiplicity. So that would be our estimate. And then if you wanted a better idea, you can find a couple of extra points. And before I freeze out entirely, let's try and get one more example in. Let me see if there's something that I like here. I guess we'll look at 16. I think that one will be okay. F of x equals, we have x minus 4 squared, and we have x plus 2 squared as well. Looking at this, if you want to write the step out, you could, but looking at this, especially when all the coefficients are 1, when you square, our first term is going to be x squared plus stuff. Our second factor, rather not term, also will be x squared plus stuff. So our leading term is going to be, a ruler came in, what is going on? Our leading term is going to be x to the 4th. So this is even positive. Because it's even positive, I know that my end behavior, both tails will go off to infinity for even positive. And I also know I'll have at most 3 turns. So at most 3 turns. And looking at this one, we saw that we have 1, 2, right? We had 2 turns as anticipated. At most 2.
Professor,
Yeah,
when you say at most 3, that means that there can be less than 3?
correct. There could be less than 3. Yeah.
In what cases?
Say that again.
In what cases there can be less than 3?
It would depend on the zeros and their multiplicity, but a good example of that, if we were to just graph f of x equals x to the 4th power, then the graph would simply look like a sort of drawn out parabola, so there would only be one turning point, right? But as we add more zeros, if we have more zeros, then there will be more turning points.
I see. Thank you.
So for now, again, without calculus techniques, we can just say, at most 3, but that's not very powerful. But it's something. It's going to get more exact as you guys get to calculus.
Got it. Thank you.
A lot of what we're going to do here is still going to be estimation of the graph, unless we turn to calculators or some graphing software, which we're not doing. All right, so here we have x-intercepts. These are going to be fairly easy to find here. We have x minus 4 equals 0, so that's x equals 4, and that's multiplicity of 2. X plus 2 equals 0, x equals negative 2, that's also multiplicity of 2. So this one, well, both of them, they will touch. They will not cross those because even multiplicity, so they will touch those zeros. For y-intercept, we will do f of 0, and that might get pretty big of a number, so we'll just kind of estimate it on the graph. So this will be 16 times 4, which is 64. 4 squared, 16, 2, yeah, 64 is good. All right, so now we'll get some idea of the graph and approximation. I'm not going to label my y-axis here. Not yet, at least. So far, we have the following. So we have 4 and negative 2. And I know that I'll be going off in those directions. Now, if I want to know whether my options are, my 64 is, let's just arbitrarily mark a point here and say this is 64. So my options are, I can come in, oh, I can't cross, right? So I have to come in, I touch, I go back, then at some point I do have to go back down. Now, I don't necessarily know if the peak happens on this y-intercept, probably not, or if it happens past it, or if it happened before it, right? Because it could have done something like that as well. So again, those things I don't necessarily know. I would have to plug in some points to get a better picture. For example, points that I would want to plug in might be f of negative 1, f of 1, f of 2. That will give me a slightly better idea of what my function does here, 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 right? But again, I'm saying that's optional, so without it, I'm just going to estimate the turning points. So I turn here, then I have to come down. Again, I cannot cross this guy because both of my multiplicities are even, so I have to touch it and then go back to infinity. So what is being estimated is this guy here. Right, there's few options as to how that could have behaved, and those options can be narrowed down by finding some of the values that we discussed. But this is a nice enough of an estimate, so we will just keep that. All right, so we got time. So I'm gonna give you guys one last example and a little bit of time to work on it. But this one is not factored. So we're going to see if you remember how to factor and then get all the other pieces of information out of it as well and try to graph it. So here we have f of x is 4x cubed plus 10x squared minus 4x minus 10. So go ahead and approximate the graph just like we did in the previous two cases, but again, this isn't factored, so you might have to remember different factorization techniques. I'll give you about 7 minutes to get as far as you can or to finish this one, and then we'll go over it.